Aloha! Welcome to our exploration of how an outdated school of psychology, behaviorism, has found new relevance in artificial intelligence. We'll delve into the fascinating journey of reinforcement learning and its impact on AI development. Reinforcement learning, RL, in AI has its roots in behaviorism, a psychological school of thought that dominated from the 1920s until the mid-1950s. Behaviorism, as its name suggests, focuses on observable external behaviors rather than abstract internal mental processes. This perspective faded in the 1960s with the rise of the cognitive revolution, which emphasized human thought and cognition. While cognitive psychologists criticized behaviorism for its neglect of mental processes, AI developers found its principles remarkably useful. Philosopher Patrick Grimm highlights that the Turing test, which assesses a machine's ability to exhibit human-like intelligence, is inherently behavioral. Alan Turing's view was clear. It doesn't matter whether a computer truly understands information. If its behavior is indistinguishable from that of a human, it passes the test. One of behaviorism's central tenets, reinforcement learning, was first conceptualized by Pavlov in 1903 through his famous experiments pairing unconditioned and conditioned stimuli to strengthen a dog's responses. Building on Pavlov's work, John Watson coined the term behaviorism in 1913 and further elaborated it in his 1924 book. Skinner expanded behaviorism in the 1970s with the stimulus-response SR model, emphasizing environmental factors in shaping behavior. According to behaviorism, learning is a mechanistic process. Rewarding feedback reinforces behaviors, while negative feedback discourages detrimental ones. Critics argue that this overly reductionist model ignores the complexity of human cognition, such as emotions, biases, free will, and individual differences. Despite its decline in psychology, behaviorism's principles found a new home in AI. The 1970s and 1980s saw foundational reinforcement learning algorithms solving simple problems like robotic control and game playing. A major breakthrough came in 1989 with Q-learning, developed by Watkins. Q-learning enabled agents to make decisions by maximizing the expected value of an action in a given state. In the 1990s and early 2000s, RL algorithms advanced further, particularly in robotics, games, and control systems. Notably, TD Gammon, developed by Tesauro in 1992, learned to play backgammon by competing against itself and analyzing outcomes. In the 21st century, RL achieved groundbreaking successes, led by companies such as Google DeepMind and NVIDIA. Google's AlphaGo, AlphaZero, and AlphaStar stand as landmark achievements. AlphaZero, for instance, acquired world-class skills in chess and Go through self-play without prior knowledge of game rules. By learning the rules autonomously and optimizing its strategy, AlphaZero defeated Stockfish, the reigning chess champion, in 2017. Similarly, AlphaGo stunned the world by defeating top Go players in 2016 and 2017, while AlphaStar triumphed over professional StarCraft 2 players in 2019. Meanwhile, NVIDIA contributed to RL advancements through specialized hardware and software, such as NVIDIA Tensor Cores and deep learning SDKs, which accelerate matrix computations essential for RL algorithms. Beyond gaming and robotics, RL also plays a significant role in economics and game theory, where optimal outcomes arise from interactions between agents. What distinguishes reinforcement learning from other machine learning approaches is its long-term optimization. RL prioritizes maximizing cumulative rewards over time rather than minimizing short-term losses. In games like chess or Go, focusing solely on immediate rewards can lead to poor long-term outcomes. RL takes into account the unforeseen consequences of moves, demonstrating a far-sighted strategy. A famous example is move 37 of AlphaGo during Game 2 against a world champion. Initially viewed as nonsensical, the move was later recognized as pivotal to AlphaGo's victory. As noted earlier, behaviorist psychology has faced substantial criticism and is often regarded as outdated. In many psychology programs today, reinforcement is discussed primarily for its historical significance. The limitations of behavioralist psychology in understanding human behavior arise from the inherent complexity of humans as biological, emotional, and rational beings. Behavioralism, rooted in the idea that behavior is shaped by reinforcement, rewards, and penalties, works effectively in controlled environments and with simpler organisms. However, when applied to humans, the model often falls short because human actions are not solely driven by immediate rewards or punishments. Instead, they are influenced by emotions, values, free will, and internal motivations that transcend tangible reinforcements. For example, alcoholics and drug addicts can persist in self-destructive behaviors despite the severe penalties they face: health deterioration, financial ruin, and damaged relationships. From a reinforcement perspective, these negative outcomes should deter the behavior. Yet addiction often involves psychological and neurochemical factors that override the logic of punishment. On the other hand, artists and evangelists frequently pursue their noble goals without any external rewards, and in many cases, despite significant hardship. Their commitment stems from intrinsic motivations, a sense of purpose, passion, or a deeper calling that behavioralism fails to capture. In contrast, machines, particularly AI systems, operate within a far more predictable and controlled framework. Reinforcement learning, a subset of machine learning, thrives precisely because machines lack the emotional and volitional complexities that characterize humans. AI systems do not experience desire, fear, or free will. They optimize behavior based solely on predefined objectives and feedback signals. For an AI agent, actions are evaluated through reward functions or penalties, and the system adjusts its behavior to maximize cumulative rewards over time. The lack of internal conflict, ethical considerations, or emotional states allows reinforcement learning to work remarkably well in machines. The success of reinforcement learning in AI highlights a fundamental difference between machines and humans. While humans often act according to subjective, emotional, or irrational impulses, machines function purely based on their programming and the data they process. Machines do not require intrinsic motivation or consciousness to achieve their goals. They simply follow the logic of optimization. However, this distinction also raises important ethical and philosophical questions. If reinforcement learning can produce machines that outperform humans in certain domains, what does this mean for the value of human judgment, creativity, and purpose? Unlike machines, humans bring a moral and emotional dimension to decision-making, one that is not reducible to rewards or penalties. While reinforcement learning allows AI systems to achieve extraordinary results, these systems remain tools. They lack the depth, meaning, and self-awareness that define human experience. The revival of behaviorism in AI highlights an enduring lesson. Never say never. Despite being declared obsolete, its principles have found new life, driving advancements in artificial intelligence. As we conclude, it's clear that reinforcement learning has transformed AI, drawing from behaviorism's legacy. Thank you for joining us on this journey through the intersection of psychology and technology. Mahalo!